so it's 8:30 and we're a little bit ahead in terms of the course schedule, as we did the binary representations and the computer arithmetic in 1 week rather than 2 weeks. So we're moving on to the von Neumann architecture and the computer stack. We should be able to get through this lecture in today, and I'll create a homework for you guys to work on Friday. And then next week we can start working on the labs rather than homeworks and lecture. So lecture, I'll be helping you with the labs, learning Arduino, and we'll have some in-class time to work on the labs. And what I'll ask of you is, if you do have a personal laptop that you can bring, please bring it, because when ITS installed Windows 11 on all these computers, they removed all of our software. So we don't have the Arduino IDE on these computers. We do have some laptops in the room adjacent here that has it, that we can grab and use. But if you have your own computer and then you can work on it outside of class to finish, that would be a more ideal situation. All right, so we're talking about the computer stack. So the idea of the stack is coming mostly from this idea of abstraction. So the more layers of abstraction that we have, that is where this stack is coming from. So we have the hardware at the very bottom, and even if we think below that, in terms of the circuits, you have like the layouts, the transistors, transistor sizing. But as computer engineers, you could know about that, and you will learn about that. But as software engineers and computer programmers, most of the time they are aware of the architecture parts, but nothing below that. And then above architecture, we have the interface between hardware and software, which is your instruction set architecture, or ISA. And above that, we have the assembly code that the compiler will create. And above the assembly code, we have the high-level programming languages that most of you are familiar with. Right? So like C code, Java, Python, those kinds of things. All right. So the other things that are common in computer architecture and also digital logic design in general is that we want to make the common case fast. So this comes from Amdahl's law. So Amdahl's law says that your performance gain is proportional to the amount of time that the performance gain is actually affecting. So that means that we'll gain the most performance by targeting the piece of our programs or workflow that is taking the most amount of time. And we can improve performance in many different ways. One is taking advantage of parallelism. The other is taking advantage of resource sharing, or making sure that we're utilizing every single resource all the time with pipelining. And the other is through prediction. And this is more of a computer architecture performance increase. But what we'll see across digital logic designs is this hierarchy of memories. So abstraction, we use it to simplify design. It's used by both computer architects and programmers, and to some extent also digital logic basic designs that have some programmability in them. So we want to represent the design at different levels so that the lower level details are hidden to offer more simple models at the higher levels so that we can be more productive. And this helps us be more productive because it helps us cope with the enormous complexity of real systems. So here are program levels. So we start with high level language like C code. This will be taken in by a compiler that will generate the low level assembly. So the assembly are the individual instructions that are run on a processor. And then in order for the processor to understand the assembly instructions, the assembler translates all of these assembly instructions into the binary machine language. And these are the instructions that the processor will read from memory that tells it what to do, every single instruction. All right. So here are our abstraction layers beyond just the software part. So we saw the software parts and how it also has abstractions around it. But there are also abstractions between hardware and software. So for software, we mentioned, right, we have the high level languages. And those are used to create programs like word processors, emails, coded, right? All of these applications that you use. And then we also have system software that is running to manage the application software. So this is going to be like your operating system. It's going to handle your input outputs in terms of your mouse interrupts, keyboard interrupts. It's also going to be managing and scheduling when the other programs are running. So if you have a high priority program that might get more CPU time proportional to the other lower priority programs, you might have specific operating systems. Like if you're writing an operating system for an embedded system where you have real-time deadlines, you would write a different scheduler than for a consumer processor, right? The consumer processor, for the most part, will try and do equal time share across all programs. But for an embedded system with real-time deadlines, that's where the scheduler is going to have this priority list. And it has to make sure that these deadlines are met in the scheduling of the programs. The software, the operating system software is also handling the memory and storage allocation. Like where in memory is this program going to be stored? Where in memory is the program's data memory going to be stored as well? Right. So on the hardware side, we have the CPU or the processor, and we need to have memory. And we also have these different input-output devices that have their own drivers that we need to write system software for. So here's our stack or the different layers. Okay. So we have application software at the top of the stack. This is where software engineers are mostly working. And then we have system software, that's your operating system, drivers for hardware, things like that. And then under that, we have the instruction set architecture. So this is the list of commands that are understood by the hardware. And then below the instruction set architecture is where we get to the actual hardware. So we have the microarchitecture, so the actual hardware implementation of the ISA. And you can have multiple different hardware implementations implementing the same ISA. So an example of this is one of the most popular ISAs is x86. x86 is developed by Intel, and it is what they are using to use as their ISA for their processors. But AMD is also making processors that have x86. Another example is ARM. So ARM is an instruction set architecture. ARM is what is used as the ISA for the microarchitecture in Raspberry Pis, in Arduinos, and now it's increasing in its scope as phones have been using ARM for a long time, and there are multiple different chip makers of ARM now, as just in phones, Google's making their own system on chip for their phones, implementing ARM, and Apple is making their own chips. They've been making their own chips for their own phones for a long time. But now Apple is also expanding from making their own chips for just their phones and tablets to now they make their own chips for their computers, right? So they started making the M1 and M2 chip are released. So M3 and beyond is still being produced. And then below the microarchitecture, which consists mostly of kind of like these blocks of standard components that are connected. So one thing that you will see in the future, we won't talk about it too much in class, are like multiplexers. So multiplexers are just blocks that are selecting between multiple inputs to an output. And there's other things like the register file, which stores all of the data that is in the pipeline. And then if you look and zoom into those individual blocks, you'll see the circuit design that is inside them. So how is the multiplexer made with NAND gates and NOR gates? How is the register file built with those flip-flops and all of that? How is the ALU designed? That's where the circuit design is. And then below the circuit design, this is also something that you will learn about as computer engineers. This is the actual circuit layout of the transistors. And what are the sizes of these transistors? How thick are the wires that are connecting these transistors? Where in the IC are these things going to be placed in relation to each other? These are all questions that need to be answered for the circuit design to be implemented. All right. So here is our checkpoint. So your code for today is 952.
I'm trying to think.
592, right?
952. Yeah, I think most of us are done thinking about this individually. So do talk to the people around you. Talk about each one, why it is important, why you think it is not part of the importance, and then resubmit if you are changing your answer.
Oh,
I mean, that'll give it to you. So that was.
oh.
You're sure. You started.
I did like half of it, and then now we got tired.
Yeah, I did like 3 problems, but it's pretty easy. It's literally just the same.
I just want to fix mine.
What? Oh, it's still not. I looked up. Did I show you? Dude, I made mine worse.
No, yeah, that's why I'm like, I'm just like. trying to
Like,
fix
I
it.
redid it, and it's longer than what I did when I was in 231 already.
No, yeah, that's why I'm like.
I think I got like worse or something.
That's why I'm
I
like.
think that highlighted girls or something.
Yeah, it's like.
You're missing like half the code. Yeah, good day, man.
I'm gonna.
Like using the color, you know, like you schedule, I work like 12 or something. But now I work
Yeah.
7 to 3. So.
Like, we've done all of them.
Yeah, it's gonna be more, yeah, so.
Oh, no, this is good.
No, 7
I
to
just
3,
did.
yeah, 7 to 3. That's like 3 a.m. So that's what I got like 6, but it's still like seeing that on those days. So at least I'm on release, I'm still like something like.
Oh. I can remember.
I was gonna bring you fast. Oh, we need to get these things.
It's really weird because like, you know, how we.
Yeah, it sounds like we are done with the peer discussion as well. So do change your answer if you were convinced to change your answer. All right, so let's talk about this individually, right? So why is abstraction important in designing a system? So we just need to check if this is true or not, right? So for A, it says it helps simplify the complexity. Is this true or false?
True.
This is true, right? Because now we can write programs at the high level with programs like with programming languages like C or Java, and we don't need to understand the underlying microarchitecture or the IC layouts or things like that. Okay. And it also makes it simpler as we don't need to write assembly code either. So going instruction by instruction, it's very hard to look at that code and understand what it's doing quickly. But for high level programming languages with for loops, if statements, you can kind of understand what it's doing rather fast. So for B, reduces programming time. Right? That's true. It goes with A, right? Because we've simplified the complexity, we're able to be more productive. So because we don't have to code in assembly, or maybe reducing our programming time by an order of magnitude, maybe more. Okay. Enables targeting different hardware more easily. I hear false. Anyone like true? I know there are some people that like true. I want to hear from a true person.
You're asking about that.
So why do we like C? Why do we not like C?
Let's talk about on Bill's law.
This one's not related to Amdahl's law.
Oh. No. Yeah, that's not Bill's law.
Again, it's asking about abstraction. You had your hand up?
I thought it made sense, but I don't know, like, for sure. I just thought that if the other two were right, that it would kind of lead towards the third one being kind of right, but I didn't have like a good idea of why I thought that.
Okay. So it sounds like we should go back to explain this. So here is the key. I write code in high level C language, right? Here, actually, let's look at it here. This is where I write code. And the compiler is going to turn it into some assembly language. And the assembly language is defined by the ISA. Okay. And the microarchitectures are implementing that ISA. So because of this abstraction layer between of the high level programming language and the compiler, I can change my compiler flags to target different ISAs. So that means my same program can run on a computer that is implementing ARM. I can compile it for x86. I can compile it for MIPS, right? So I only have to write the program once, rather than 3 times over for these different ISAs. So because of this abstraction between the programming language and the assembly, we're able to target these different hardware platforms without rewriting code. So that's why it would be more easily. That's all because of this abstraction. Okay. So that's why we like E. So it's A, B, and C. Right. So in terms of computer architecture for general purpose CPUs, The focus is on the instruction set architecture and the machine organization or the microarchitecture. So this is the hardware software divide, and that's where computer architecture is focused on. So in terms of the instruction set architecture, this is the lowest level of software interfacing with hardware because it's right on that divide. And like we talked about, it's the set of assembly language commands that the hardware can perform. It also defines the different items available inside the machine organization or the computer architecture that are available to the program. So what are the data types? Are there integers? Are there signed integers? Are there floating points operations? What are the different registers? How many there are? Are there different addressing modes as well? So there are a lot of key decisions when you're making the ISA. It's like, how many operations should you have? Which operations should you do? How complex should these operations be? And then going on that idea of how complex the operation should be, we go back to Amdahl's law, right? We want to make the common case fast. So if we're adding operations that are specific for some program, and it's making our architecture more difficult to implement because we have to optimize for that instruction that is not used very often, that's often going to hurt the performance of other programs overall. So that's where we want to have the simplest operations that we can have so that we can optimize for those. And if a program needs to make a more complex operation, it can use these simple operations to build up to make a complex operation. And then how many operands should we have? Where are they in the processor? Are they the register? Are they in memory? And then what are their types? Are they floating points? Things like that. And then once we have the operations and operands, we want to ask again, what are the different formats of our instructions? How long should the instruction length be? Should we have variable instruction length? So all of these questions you have to answer when you're making the ISA, kind of before you're even making the microarchitecture that is implementing that ISA. So that is one thing that we've talked about a little bit before. The x86 ISA is very complex. The reason that we have kept it around and keep releasing new processors, like Intel and AMD are still releasing processors that implement x86, is to make sure that all of our previous programs that were already compiled can still work. But because they were unaware of that simplicity was the key to computer architecture, there are a lot of complex instructions that are implemented, and it's leading to a wider performance gap between x86 and more simple microarchitectures that are implementing ISAs like ARM or RISC-V. So that's one of the reasons that we can see that, say, Apple's M1 chips are a lot more energy efficient than Intel's chips. The performance is similar, but the energy efficiency is one of the key differences. Right. So the microarchitecture, this is the hardware implementation of the ISA using those functional units. So the registers, how many there are, to ALU. This is implementing all of your arithmetic instructions like add, subtract, multiply, divide, bitwise and. You have shifters and logic units. So the logic units are those things that I was talking about, like the multiplexer. So the design issues are, how are these units connected? How is the data going to flow through? And how are we going to create logic units that control this flow? So here are our examples. We have all of these Intel chips, and we have an AMD chip. And a microarchitecture is usually implementing a specific ISA. So we have Intel's Core line, AMD, they have their Zen line, they have their Ryzen line. So the Zen line is just short for Ryzen. They also have their EPYC line. Intel also has their Xenon line. They're all implementing x86. And then this processor is implementing ARM. And on a Raspberry Pi, it's an ARM Cortex. So that is implementing ARM. And Apple's M1, M2, and their A line of chips, they're like on A15 or something now, I don't know. Those are implementing ARM. So this is one of the key ideas in your architecture as well. And it's across all of the different types of computers. So desktop servers, embedded computers. If it's general purpose computes, and for the most part, even ASIC designs, you have this load stored program idea, which is the von Neumann architecture. You have the memory where you're storing your program and all of your data. And then you have the processor that is going to operate on that data. But in order for it to operate on the data, we first need to move it from the memory into the data path. So we need to load our instruction, figure out what the instruction is. And if the instruction is loading data from the memory into the data path, we need to grab that. We need to work on it in the data path. And then when we're done, we need to store it back into memory. So it is this stored program and stored memory that is the von Neumann architecture. So like I mentioned, this is very widely used, but we are trying to explore different architectures that move away from this in order to achieve better energy efficiency, better performance, because we do have the end of Moore's law. And also a lot of the time, especially for big data applications, like machine learning could be an example, the moving of the data from memory to the processor can be a lot of energy wasted. So some machine learning workloads will be very data heavy, and in processors, usually load word, store word are the most energy intensive instructions. So in order to kind of remove that overhead of the stored program and stored data architecture, we're exploring things like processing in memory. So not moving the data. We process directly where the data is stored. So that is, again, like I talked about, one of my threads of research. Right. So we can start looking at some devices. So we have user interfaces that are part of the device for input and outputs. You have displays, keyboard, mouses. Yeah, these all have their driver software, which is running at the operating system level because they need to be able to interrupt so that you can get responsive user inputs and outputs. You have storage devices. So this is where you're going to store your programs, your data, your pictures, right? And then we also have network to communicate with other computers. Right. So memory, there are two main types of memory. So there's non-volatile memory. This is able to hold more data. It's usually more dense and cheaper. So you have magnetic disk, flash memory, you have optical disk, and there's also magnetic tape. Okay, so magnetic tape is still used for archival storage, but it is very low performance because you need to physically unwind. So it's good if you never need to touch it and you're just trying to store it. But for the most part, we're moving more and more towards mostly flash memory as the density is becoming more and more, it's larger and larger and it's cheaper. There's also, so non-volatile, the other thing about it is you don't need to power it. Once it is stored for a reasonably long amount of time, for magnetic disks, this is like thousands of years, it will not lose that data unless it is destroyed. And then for flash memory, it's more on the order of hundreds of years because they do discharge, but it takes a long, long time. So that is why we consider it non-volatile, because they do not need to be powered to keep their data. Turn the computer off, the data is still there. But volatile memory, as soon as they lose power, they start discharging and everything becomes zero. So this is used as DRAM, which is your computer memory, as well as SRAM, which is for your caches and your registers on the processor. So we have this memory hierarchy. We have registers and cache at the top with SRAM. It is very expensive and very small. And as we keep going down this stack, this hierarchy, we get cheaper and larger. So main memory, which is DRAM, it's cheaper and more dense than the SRAM. And then we can get to flash memory, magnetic disks, and then optical disks, and magnetic tapes. And the reason that we have this is we need very fast memory storage in order to have good performance, but it's not feasible to have very large memory storage that is this fast. Your chip would just be way too large. And so we have this hierarchy. So if it's not available at the higher tiers of the hierarchy, you have to look down until you find the data that you need and move it up. All right. So as again inside the processor, so this is on the chip itself. We have a data path that performs operations on the data and the control that is going to determine which parts of the data path are activated, not activated, where the data is going to flow through. And we have a cache, which is our small and fast memory that we're currently working on. And then when we are done with it, we put it back into the main memory, DRAM. And before we shut down the computer, it moves from DRAM to be stored into the non-volatile memory if it was supposed to be stored. Right. So this is the last checkpoint for today. And just use the same question one just change your answer to your answer of this question. Okay, so it sounds like you guys are starting your peer discussion, so do continue this. And when you are done with the peer discussion, if you do change your answer, do change your answer.
Yeah.
I think it's smaller, it's more expensive. It's less expensive. Or so. Technically, it's both. It's the direction we go. Not sure currently. Like this.
Okay, so I think you guys are mostly done with this discussion. So again, let's go through this one at a time. So complexity of accessing data. Does this memory hierarchy reduce the complexity? I see yeses and nos. So what do the nos think? Why?
Take that out because you're gonna be using a lot of different types of memory.
Uh-huh.
And because it has to jump between like from main memory to like registers for processing and back to main memory. That's complexity.
Mhm.
Whereas. I can't. Okay,
Opposed to one large thing, right?
yeah,
So
that would be too big.
it does increase the complexity of accessing data because now you have different nodes. If you had one big, large memory, it wouldn't be feasible, but it would be less complex. You would just have one place to look. But with the hierarchy, we have all of these different places to look. And if we don't find it in the higher level, we have to search the lower level. Okay? So it is more complex with the memory hierarchy, but it does improve performance. And then B, cost. Do we reduce cost?
Yes. Types of-
Yep. Because
We wouldn't have as much
Yeah.
of that upper.
because now we can have a smaller amount of the really fast and less dense memory and more of the cheaper and more dense memory to store the programs longer term. Processor area. Are we reducing this?
Yes, because we're not gonna have as much of the upper.
Yeah. So because the top of the memory hierarchy is what is actually directly on the processor, we can have less of it by having this hierarchy, and that will reduce the amount, the overall size of the processor. And I'll show you how that looks in a couple of slides. But this is BNC, right? We reduce cost and we reduce processor area, but we increase complexity. So this is the example we're going to look at, an iPad. And this is the A12 Bionic. So again, this is implementing ARM as its ISA. And here we can see it has 2 big CPU cores. And next to those CPU cores is the L2 cache. So again, this is on chip. So this is SRAM. And you can see it is just looking at the core itself. It's about the same size, right? So, and this is only in the order of megabytes in terms of storage capacity. So just imagine if it was in the order of gigabytes, which is what we use, right? It would just be enormous, 1,000 times bigger. Your CPU would be the size of your monitor. Wouldn't work. So we need the memory hierarchy. And then here we can also see that they have these different smaller CPU cores, and they have this shared cache. And there's 4 more banks of cache that these GPU cores are also able to access. And then the rest of the die area is for interfacing with the lower levels of the memory, so DDR. So this is DRAM. And one other thing on the A12 Bionic is it has this NPU. So the NPU is a neural processing unit. So this is an accelerator. Because in order to get real-time feedback of their machine learning applications, they can't run it on the CPUs. The CPUs have way too much overhead, and it takes way too long to run the application. So they're building this accelerator, which is kind of like an ASIC design to make their machine learning applications run faster. So like this is the activation of Hey Siri, things like that. All right. So this is just the increased capacity of transistors over time. This was Moore's law, that we would quadruple capacity every 3 years, or really the main thing that he was saying was double capacity every 1.5 years, but this is the same thing, just in a longer time scale. But again, this has slowed down significantly, and it has almost flattened because we have made the transistors so small that they are becoming closer to the size of the molecules themselves, and they're becoming more and more unpredictable once you go to that scale. So we can't make them any smaller, so we don't get any more energy efficiency gains by going smaller, and we don't get any more performance by having the ability to put more transistors on the chip. So that's where we are building accelerators and like that. Okay. So that is all for today. On Friday, we'll have time to work on the next homework. And your homework 3 is due before class on Friday. And again, you can submit as groups. So if you are submitting as a group, just submit one, but make sure that you add your group members. And I think for some of the submissions, homework 1 and homework 2, there are still some group members that were not added that should be added. So do that so that I can move the grades from Gradescope to Canvas.